Alright guys, in this video we're going to talk about differential equation FRQs. So what is a differential equation FRQ? A differential equation FRQ is one where they give you a differential equation, and usually somewhere in the problem they'll give you an initial condition. Okay, so they'll start off with something like this, for instance. You don't need to write this, but this is a differential equation. And they may give you some kind of an initial condition, like they might say f of 1 equals negative 1. Okay, a lot of times we have some pretty predictable types of questions that they'll ask out of those, and here they are below. They may ask you to sketch a slope field, sketch a particular solution, do a linear approximation, etc. And here are the points that they typically ascribe to those types of questions. So what I'm going to do is I'm going to do one type of question from each one of these in this video just to kind of show you what those look like. All right, so let's go ahead and get started here. All right, so here's our first one, 2005. It should be pretty close to page 28 in your blue books. Notice that it's question 6, which means we should not be using a calculator on this particular question. All right, so let's go ahead and begin the process here. So here's my differential equation that they gave us. The first thing that I want us to look at is sketching a slope field. For those types of questions, they're basically just plugging numbers in for each coordinate, finding the slope, and then sketching the slope. And those are usually worth 1 point. They're not worth a whole lot, and they can take some time. So, you know, budget your time as you see fit, but on the plus side, they're kind of easy to do. They just take time to do. All right, so let's begin here. I'm going to start with this first point here, and the coordinates of that point are -1, 2. So the x value is -1 and the y value is 2, and I'm going to plug them in here to find out what the slope is. This will give me the slope because it's the differential equation, which gives me a slope. So we have -2 times x over y. The x value is -1 and the y value is 2. So I have 2 over 2, which is 1. Now what's important when you sketch the slope here of 1 is that you notice that it's positive. Positive slopes go in that direction, up and to the right. Also, for a slope of 1, that's about 45 degrees. So if you imagine this is like a 90-degree angle, 45 degrees is right in the middle. Okay, so that's what a slope of 1 would look like. So a slope of 1 would look like this, give or take, okay? And we're just going to keep doing that for every point. Sometimes, if the more used to these problems you get, you can start seeing some shortcuts that you could take because of symmetry. Let's go ahead and do the next one here. I'll go ahead and do this point. The coordinates of that point are 0, 2. Now, something that I notice about this particular question is that the x is 0, and therefore you end up with 0 over 2, which is just 0. Now that's going to happen anytime the x value is 0. And the x value is 0 for all of these points here on the y-axis. Maybe not here. You got to be careful here because now the y is 0 also, and you'll see what that'll do in a minute. But for now, anytime the x value is 0, the slope is 0, which means that we're going to have a flat slope here, a flat slope here, and a flat slope here. Once again, I'm not going to put one here yet because we'll see what happens there because at that point y is also 0. So things get a little different. Let's go ahead and take a look at another point here. We have that point. The coordinates of that point are 1, 2. Now in that case, I'm going to get -1. Now that's a 45-degree angle also, but negative angles go down as they move to the right. So it's going to have the same steepness as this slope here. It's just that it's going in the opposite direction. Now, something that you might notice now is that there's going to be like this symmetry thing going on. On this side, this coordinate has the same thing as this side. It's just that one of the numbers is an opposite sign, which causes this whole thing to come out to be the same thing, just an opposite sign. So now as a shortcut, I could worry about only finding one side and just do the opposite on the other side. So let's put that into practice here. Let's do the next one. For this point down here, the coordinates are -1 and +1. So plugging that in, I get a slope of 2. Now, if a slope of 1 had a 45-degree angle, then a slope of 2 is going to be steeper than that. So I would say like a slope of 2 might look maybe a little bit more like this. And this one over here is going to look the same, it's just going in the opposite direction. Okay? Now, for the next points here, now they don't even really want us to find any slopes at these points here. Notice there's no dot there, so we don't have to. But the reason for that is because the y values are 0, so if you were to plug 0 in, you'd get 0 on the bottom, which means that the slopes are non-existent. Technically, you could draw a vertical line there, but I would not, because they don't even want us to do that, so I'm going to leave those off. Okay, but just so you guys know, there's undefined slopes here, and that's why I didn't want to put a horizontal line here. Let's go into the last one here. This point, we have -1 for the x and -1 for the y. So plugging that in, we end up with -2. So it's going to look like this one. I've already sketched a -2 slope over here. So it's just going to be the same. It's just down here now. So that's going to look like a steep line going in that direction. And this one will be opposite, as we said, because of the symmetry. And there's our graph. All right. Let's see how they grade these types of questions, part A. So it looks to me like they give 1 point for the 0 slopes. Did you get the 0 slopes in the right spots? Also, did you get your non-zero slopes approximately right? Notice how these ones are just barely steeper than these ones. I don't think they really care too much about the relative steepness. I think what they're really just looking for is making sure that this is positive and these ones are negative, these ones are negative, and these ones are positive. So long as you had them going in roughly the right directions, you would probably be good. And I said it was worth 1 point, but they actually made this worth 2 points. So there you go. It could go either way, I guess. Let's go ahead and take a look at part B. Well, actually, let's not. Let's back up a little bit. Let's look at a different type of question here. Sketch a particular solution in a slope field. Now, for this one, my strategy suggested to you is leaf in a river. And I'll explain what I mean by that in a minute. But typically, these questions are only worth 1 point. So let's take a look at a problem that's like that. All right. So this one's the 2014 question. It's probably pretty close to page 42 in your guys' blue book. It's a number 6. It's a no calculator question again. So let's go ahead and take a look at it. So we've got our differential equation. We have an initial conditions. So that's how we know we're looking at a differential equation type of question. And then part A. A portion of the slope field of the differential equation is given below. Sketch a solution curve through the point 0, 1. So sketching a solution point at the point 0, 1. So we want to find this point first, 0, 1, and put a dot there. 0, 1 would be right about here. Now a solution curve, how do we do that? Well, my suggestion to you on the little reference sheet was think of like a leaf in a river. Think of these lines as the current of a river, and think of your dot as a leaf that you've just dropped in the river. Well, it's going to follow the current. So it's going to come up and it's going to go down like that with the current. Or if we were flowing in the other direction, it's going to come over here like that, and then it's going to shoot up like that. So that's what I mean by leaf in a river. Basically, once you put your dot in there, it's going to determine the direction of your curve and the shape of your curve. And this is what we would call a particular solution. All of these slopes represent all the different possible slopes given by this differential equation. But with this initial condition, that is the particular solution that would result. Okay, so that is sketching a particular solution. Let's see how they would grade that. Yeah, and sure enough, they're just giving 1 point for it. I do think that they would want you to go all the way from one end of the graph to the other. I don't think they would want you to only like go this far or something. That wouldn't be good enough, so make sure you do go as far as you can with them. But that's it. Let's go ahead and move on to another type of question. Linear approximations, also estimating values. So for these ones, they want you to find the equation of a tangent line, which means you need to find the x, y, and m. The x and the y will be the initial condition that they give you. The slope can be found by plugging the initial condition into the derivative. Then you set up this little formula here, and then once you have that, you can use it to estimate a function's value. And these questions are typically 2 to 3 points. Let's go ahead and take a look at a sample of one of those types of questions. So back to FRQ 2005, pretty close to page 28 in your guys' blue books. This time we're going to be doing part B. Now, let's read part B. It says, let y equals f of x be the particular solution to a differential equation with the initial condition f of 1 equals -1. Now, just as a side note, on our last in-class test, a lot of you guys looked at this type of question, and you assumed it was the kind where you have to integrate it to find the particular solution, because you saw this word here, particular solution. But that's not what's going on here. Look at the directions. Write an equation for the line tangent to the graph of f and use it to estimate. This is the important part of that sentence, okay? Y equals f of x is some unknown particular solution, but that's not what they want you to find. They want you to write an equation for a line tangent to the graph of f at 1, -1. So for these type of questions, this is my initial condition. So x equals 1, y equals -1. Now we need to find our slope, and to do that, you plug your initial condition into the slope formula. And I end up getting 2 as my slope. The next thing I'm going to do is I'm going to write out my tangent line formula. Slope goes here, the given x value goes here, and the given y value goes here. And then the third thing you do is you estimate. So I want to figure out what is f of 1.1. Well, since the tangent line is an estimate of the actual function, which we don't know, f of 1.1 is approximately equal to y of 1.1, which means that we have 2 times 1.1 minus 1 minus 1. And since this is an FRQ, I can stop here and be done. Okay, so that's how you do those. Let's see how they would grade that, part B. So the line tangent is this. Now they wrote it a little bit differently, but it is the same answer. We would both get the same amount. So you get 1 point for finding your tangent line. And they also give you 1 point for finding your estimate. Okay. Now, sometimes this is worth 3 points, because sometimes they'll give you a point for finding the slope also. But in this case, they did not. So like I said, 2 to 3 points is what we're looking at for linear approximation questions, which is what that one is called, a linear approximation. Now, another thing you could do with a linear approximation is you can use that to decide whether a function is concave up or concave down. So if the actual function's value is greater than the tangent line's value, that means the function's concave up. But if the function's value is less than the tangent line's value, that means the function is concave down. So let's go ahead and take a look at an example problem like that. So let's go ahead and take a look at page 34, or somewhere pretty close to that, for FRQ 2010, and we're going to be looking at part B. Now, part B says use the tangent line equation from part A to estimate f of 1.1. Well, I haven't done part A for this, so I'm just going to cheat and steal the answer because we've already practiced that. We don't need to practice it again. So here's our tangent line. Y equals 2 plus 8 times x minus 1. So let's write that out. Y equals 2 plus, is that what it was? I'm sure I read that right. Yep, 2 plus 8 times x minus 1. Okay, so there's my tangent line. So they said, use the tangent line equation from part A to estimate f of 1.1. So f of 1.1 is approximately equal to y of 1.1, which is equal to 2 plus 8 times 1.1 minus 1. Now we could leave it like that, but I think it'll be helpful for the rest of this to actually simplify it. So we have 1.1 minus 1 is 0.1. 0.1 times 8 is going to be 0.8. and 2 plus 0.8 is 2.8. And so there's the answer for the estimate. Okay, so we've answered this much of it, but that's still nothing new. We want to get into the part where we look at the concavity and how that relates to these estimates. So they're telling me that f of x is greater than 0. Now another way you can think of that is that means that y is greater than 0 for all the values of x between 1 and 1.1. Now why is that significant? Because our tangent line is at the point x equals 1, which would be a little bit more obvious to us if we did part A, but that's where we did our tangent line, was at x equals 1. And then we're doing our estimate at 1.1. So from 1 to 1.1, our tangent line is in view here. Okay, so now the actual function is always positive on that interval. Now their question is the approximation for f of 1.1 greater than or less than the actual value of f of 1.1? Well, we don't know what the actual function is yet, so we don't know. But here's what they're asking. They're asking, is this true? Or is this true? We know that the estimated value is 2.8. And so the question is the actual value greater than that, or is it less than that? Now, for the top case, if the actual function is greater than the estimated value, that means we're dealing with concave up. If the actual value is less than the estimated value, that means we're dealing with concave down. And so if I want to know which of these it is, I need to know whether my graph is concave up or whether it's concave down. Now, how can we tell what the concavity of a graph is? Well, one way you could do that is by looking at the second derivative, which they just so happen to give us here. Okay? Now, is the function, the second derivative positive or negative? I'll just put f double prime. Is it greater than 0 or is f double prime less than 0 on the interval from 1 to -1? Because if it's greater than 0, that means it's concave up, which means that our actual value is greater than our estimate. Or if the second derivative is negative, that means my graph is concave down, which means that the actual value is less than the estimated value. Okay, so now my question is now, what is the second derivative? Is it positive or negative on this interval? Well, we know that on that interval the y value is positive. So let's look at this. We have y cubed. Well, if y is positive, that means that this would be positive, right? Then we have 1. Well, 1's a positive number, so we can just put a positive there. Plus 3, x squared, y squared. Well, squares are always positive. So we have a positive being multiplied by a positive plus a positive. Well, what do you think that means? That means that the second derivative is positive. So since my second derivative is positive, that means my graph is concave up, which means that the actual value f of 1.1 must be greater than the estimated value at 1.1. So this is all a bunch of work and a lot of thought, but how would we word it here? Let's go ahead and write that out. So here's one way to write out the answer. Let me see if I can move this down a little bit. There we go. So since f is greater than 0 on the interval from 1 to 1.1, the second derivative is greater than 0 on that interval, and therefore f is concave up on that interval. And since f is concave up, the actual value must be greater than the estimated value. Okay, and that's kind of an example there of how a tangent line can be used to determine the concavity of a graph or vice versa. So sometimes, you could be told the function is greater than the tangent line, and from that you conclude it's concave up. But it could also go the other way where you say, well, it's concave up, therefore this must be true. This is a biconditional statement. It can go either way. So, but that's basically the principle there. Anytime your function is concave up, the tangent line is going to be an underestimate. Anytime your function is concave down, the tangent line will be an overestimate. So that's just the relationship between concavity and tangent lines. Now let's get into the really important type of question here, finding particular and general solutions. These are the problems that we practiced in class quite a bit, and it's a 5-step process, and they're worth a lot of points, okay? So here's our steps for finding particular solutions. The only exception is if they ask for a general solution, you don't need to do steps C or D. But let's go ahead and take a look at an example like that. I think we could stick with the 2005 FRQ that we had earlier. So once again, the FRQ for 2005 is going to be pretty close to page 28 in your blue books. Question 6, no calculators. Here we go. So this one actually is asking us to find a particular solution. And those are the types of questions. When they're asking you to find a particular solution, those are the problems where you do that 5-step process. So the first step is to separate your variables. So I want to get the y's together and the x's together. So the first thing I would do here is I'd multiply both sides by dx. If I multiply the left side by dx, the dx's cancel and I'm left with just dy. If I multiply the right side by dx, I just have a dx over there now. The next thing I want to do is I want to get this y on the other side. So to do that, I'm going to multiply both sides by y. If I multiply the right side by y, the y's cancel. And if I multiply the right side by y, I have this. Now, I don't want you guys to think that it's always just multiplication. It could be division. If you want to move something from the bottom to the other side, you multiply it. But if you ever want to move something on the top to the other side, you would have to divide it. Okay? But in this case, I only had stuff on the bottom that I wanted to move, so I just multiplied. So keep that in mind. It could be multiplication or division. Those are pretty much your only two options there. Every once in a while, you end up with a really weird problem that may be looking something like this. You don't need to write this because that's not part of this problem, but I just want to show you. And if you end up with something like this, some of you guys might be really tempted to add the y. You can't do that. That's not allowed, just so you know. But what you can do is you could still multiply the dx to the other side. And then, if you want to get that y to the other side, what you could do is you could divide this whole thing to the other side like that. And that's how you would get them separated. Okay? But you can't just add one variable to the other. That's a no-no. All right, so that's step 1. And that's typically worth 1 point, is separating those variables. The next step is to integrate both sides. Now, luckily, both of these problems are pretty simple to integrate. Sometimes they could be quite complicated. Integrating the left side, we get y squared over 2. Integrating the right side, we get negative x squared plus y, just using the basic power rule. But typically, they'll give you 1 point for each one of those integrals. So now we're up to 3 points. The third step is to solve for c by plugging in the initial conditions. So I'm going to plug in 1 for x and negative 1 for y. And from there, we can solve for c. Now you got to be careful here. When you square this, you're not squaring the negative. The negative's still there. So that's really a negative 1. I just realized that this is the question I gave you guys in your test last week. I saw quite a few of you guys at this point turn the negative 1 into a positive 1. You shouldn't have, because you're not squaring the negative, you're only squaring the 1. So a lot of you guys ended up with the wrong sign, which gave you a slightly wrong c there. If you add 1 to a half, you end up with 3 halves. And so my c value is 3 halves. All right, so now we have y squared over 2 is equal to negative x squared plus 3 halves. And that's my particular solution. We have one last step now, which is to go ahead and solve for y. So the first thing I would do is I'd multiply everything by 2. If I multiply this by 2, the 2's just cancel, so I'm left with y squared. And then multiplying this side by 2, we get negative 2x squared plus 3. When you multiply this one by 2, the 2 on the bottom cancels. The next step is to square root both sides. And you have to remember that when you square root both sides, you do get a plus and a minus answer. Now, for these types of questions, you can't have both of those there. You have to pick, is it positive or negative? The way you could tell is by looking at your particular solution. Notice that my y value needs to be negative. Well, the only way that this y value can be negative is if I choose the negative number outside there of the radical. So here is our particular solution, and that would be worth the final point there. So about 4 to 5 points altogether for these types of questions. All right, but that does it. So that's differential equation problems in a nutshell. Of course, these problems can have some different things added into them, but those are the most common types of questions that you can expect to see. I'd highly recommend that you practice a lot of these types of questions. So I would recommend going through your blue books and just finding problems where you have to find particular solutions and just checking out the answers online, making sure that you know how to do that well, because not only are they really common questions, but they're high point value questions. So definitely worth your time. All right, guys, so that's it, and we'll be doing the next one later. See you then.